In this video, I'm going to demonstrate how you can calculate spectra from measured data so that you can obtain the same quantification from two different instruments. When we perform a quantification by XPS, we calculate the percentage atomic concentrations. And these are obtained by measuring photoemission peaks, their areas, so this provides the raw area, and then we divide it by a sensitivity factor. And the sensitivity factor is to account for essentially four different aspects of the data. We've got the transmission, which is a factor that is introduced by the instrument. So the transmission of the instrument varies as a function of the kinetic energy of the photoelectron. We also have, if it's a bulk material, a correction that has to be applied for the escape depth that changes as a function of the kinetic energy also. Photoionization cross-sections are dependent on the photon and the core level which is being excited. So we get different intensities for the same number of atoms depending on the photoionization cross-section. These have been calculated by people like Schofield for aluminium and magnesium anode X-rays, and these are tabulated and can be added from an element library to produce a quantification. However, we also have to account for the fact that some instruments have different geometries and electrons emitted from the surface don't all emerge in the same numbers in all directions, so we have to allow for the angular distribution correction of these photoelectrons, which will be a function of the geometry of the instrument. It's the relationship between the X-ray source and the direction of the analyzer. So we put together all of these components to these sensitivity factors. We then take the peak areas and we divide by the sensitivity factors to get a normalized area, which is then summed to give us the total signal, and therefore we can then produce the atomic concentration as a percentage. If we're measuring a sample using two different instruments, then the sensitivity factors must have components that are instrumental dependent. The transmission function, as I said, is the major component. There is also the angular distribution issue. Both instruments that I'm going to use, I believe, have the same geometry. So the only thing that I'm going to concentrate on is calculating a transmission function, and I will use the same escape depth correction and the same relative sensitivity factors based on Schofield cross-sections. So to proceed, I need to calculate the transmission functions for these two instruments. One is the Escalab 250XI that's at Poe University, and the other is a Nexus G2 that's at Edinburgh University. The first thing I'll do is calculate the transmission functions for these instruments, and I'll do that by making use of data that were acquired from a gold standard that's delivered with the instruments. So both instruments have the same gold standard, and so we can measure the spectra at different pass energies, and for each one of these spectra there are a set of regions defined, and these regions will be used to calculate the transmission function. And if I go and look at the Escalab, you can see that the exact same experiment has been performed and the same regions defined. To calculate the transmission function from these regions, we use the intensity calibration option on the spectrum processing dialog window. It's simply the case of selecting the VAMAS blocks that have already got regions defined, and then we can use the button that says compute coefficients from regions in the selected VAMAS blocks. So I'm selecting between 20 and 200 eV pass energy, and we'll press the button. We end up with a transmission function, and that's what it looks like for the Escalab. So let's do the same for the Nexus. Select the VAMAS blocks 20 to 200 and then press the button. And we end up with two new files that contain the transmission function for these two instruments. Next, I'm going to save these transmission curves, and they are VAMAS files. So if I say save as, and I see the file name, it contains lots of information, so I know where it came from, but what I would like to do is save it with a file name that is significant for other activities within adding transmission functions to these data. So I'm saving one as a TF underscore, and then this is the name of the instrument that was in the original AVG files. The lens mode is standard mode, and if I save that file, I have now got a record of this calculation. So let's now go to the other one. Here it is. This is for the Escalab, and I will then save as. And again, I'm going to delete the file name. It's useful to know where it came from, and it is a transmission curve, but I'm going to save it as a transmission function file. I don't need to have the date on this. That is also for bookkeeping. So what I want to do is now save my transmission file that tells me it's an Escalab and it's the standard lens mode. So that's good. We'll save that, and then I can close this. So if I want to apply these transmission functions to these files, doing it manually, I can do it by using an option on the spectrum processing intensity calibration property page, and that is add a transmission function from file. To apply the transmission function to a set of VAMAS blocks, I need to select the VAMAS blocks, make sure I know the origin of these data, and these are the nexus that is in the file name, and then I can choose one of these transmission function VAMAS files. So there's the nexus one, and that would be for the Escalab. This one is the one that I need, and when I select and say open, then what happened is the transmission function was updated. And how do I know it was updated? Well, it's in the VAMAS block comment. So whenever a transmission function is updated, it will add to the VAMAS block comment a statement to that effect. So here we see we've got the Nexus G2 standard TF file was applied to these data. Well, the first one anyway, and I presume also for all the others. So let's see what happens when we do a correction for the transmission for these data. So that will align the spectra in principle. So let's apply the transmission function and propagate that result. Apart from the pass energy 10, we have alignment. So that's very good. We now have equivalent spectra from all the different pass energies. We can see that they are different pass energies because the resolution of the gold for F changes. So that's the first step to getting quantification identically obtained from both instruments. The fact that they all align in one file is not a sufficient condition to say that we will get the same quantification from both files. So that's the next thing I need to show. The next step again is going to be to perform the same operation on the Escalab data. So we've got spectra that are corrected for the transmission function for the Escalab on the Escalab data. So there's the Escalab data. Let's select and open the appropriate transmission file. There it is. Select and open. Let's just verify once again that we have at least one. Yes, it's updated the first one, so we'll assume it's updated all of them. And we can perform the same intensity adjustment. So we're going to divide each one of these spectra by the transmission function and do that for all. So let's see again, what we have is good alignment for everything other than pass energy 10. So what we want to see is that these are looking the same as these, that is to say the Escalab and the Nexus data all ought to be identical for the different pass energies. So let's overlay these and have a look. Well, that makes it difficult because they are at different intensities. So let's just put up a normalization point, and what we can can do is go to the y-axis and increase the number of data points used in the point that it is normalized. That will make it slightly easier. So we can already see that pass energy 10, neither of them agree with the other spectra, so it's not surprising that these don't align. And then we get quite a good alignment for the pass energy 20 and 30, and I keep going, but you can see that there is a difference emerging here. You can see over here how the spectra are deviating, so they're not entirely equivalent. So how will we go about constructing the transmission curves that will fix it so that they both produce the same answer? If we get the same shape from our goal spectra corrected for the transmission, then we should get the same quantification. And as it stands, it looks like the one is not performing with the same efficiency as the other at lower kinetic energies, higher binding energies. So in order to correct the spectra so we get the same answer for quantification from both instruments, what I'm going to do is construct a relative transmission function for one of these instruments. So I'm going to assume that the Escalab 250Xi is closer to the true transmission than the Nexus G2, and then I will calculate for the Nexus G2 a set of curves, one for each one of these path energies, that represents the relative transmission to the Escalab 250Xi. If I choose the spectrum that is the path energy 40 spectrum from the Escalab, better get the right one, there it is, try that one. So we'll select that spectrum and use the spectrum processing dialog window and the calculator property page. I'll set that as the operand to the calculator, and then I'm going to divide all of the spectra from the Nexus G2. I'm going to divide by this specific spectrum. So let's go back to the data for the Nexus, and we need to make a selection. But before we can make a selection, what we ought to do is return these to the unprocessed state. So we've taken out the division by the transmission function, and what I want to do now is divide by the operand that I've just set. So let's do that, and then I will copy. So let's return these to their original state. Use the reset button, and I've now got a set of curves which, if I take off the normalization, I can see, especially if I zoom in and avoid the unnecessary signal from where we're dividing by very small numbers. So these are the types of shapes that will be needed to correct the Nexus G2 spectra for these path energies so that they will align with the path energy 40 Escalab spectrum. So we can see there are shapes in these data that are not very useful when we're trying to calculate transmission functions, because we would like to have smooth transmission functions that account for the fact that we've got these oscillations, that this is where the photoemission peaks were in the original spectra. So the different resolutions have produced these anomalies in the intensities. So I'm going to try and remove these by focusing on one that I think is most problematic, and there it is. So let's see if I can do that. That involves eliminating the part of the spectrum that is influenced by the peaks. And I can do that by creating regions. Let's just set a background type that will not interfere too much with the visualization of what's happening. So I'm going to identify different parts of the ratio of spectra that I think are well behaved and away from peaks. So that's my first region. And let's try and identify another region. I think we can probably go for this point, and let's find another place I can apply a region. So let's go here. And then finally I'm going to look into this area. I'd like to have some sort of region here. So I've got 4 regions I've got to find, and they're trying to span the entire energy range of these data. I've got the same name everywhere here, so let's just make all these names the same but with the label added so that they are unique, and then I'm going to propagate these to these other spectra. So let's have a look at how this works. So if we go down this list, we can see how, for the most part, we have a reasonable definition of signal that is not involving photoemission peaks. The next step is to extract from these data these regions, so I can then construct a set of VAMAS blocks that I can then fit with the closed form that will approximate these transmission functions. So let's do that. I've overlaid, and I can use now the spectrum from regions option that will extract from these spectra a set of regions. So there they are. I've now got a set of regions, and you can see here, now I go down the scroll list, you can see how I've pulled out bits of background that are relevant to the transmission and avoid, for the most part, peaks. They're all organized in the format that will allow me to merge these data. I will then merge these into a set of VAMAS blocks, and these are the VAMAS blocks that I can fit with a new curve. The option that I will use is on the intensity calibration property page, not surprisingly, and it's this option here where I can calculate, I can create a transmission function from the selected VAMAS blocks, and I'm going to fit a polynomial of a degree, which I think is enough to fit the data, but not too much so that it causes wild oscillations which can occur. So this is a balancing act of the degree of the polynomial, but if I apply this to these data that are selected, we will end up with a new file, and the new file now contains the transmission curve that's calculated and the data. So if I overlay these, you can see that the fit is reasonable. You can see that there's a plot, there's a blue curve that represents the analytic form, the closed form, and then I can step down and see how well it has performed throughout this set of data. Now we can see that there are some anomalies here associated with the higher pass energies, and maybe they're true, maybe they're not so true. Maybe we would have to do it again if we don't like the result. But let's have a look and see how well this is performing by applying it to the data, which involves once again saving these data. And I've got a file name, tells me where the calculation came from, and there's the TF, and it's a standard, and I'm going to call this one a different name. I'm going to call this Rev2. So now that I have this file, I can go back to my Nexus data. In fact, let's close this now and open the file afresh. Gold spectrum here, and that's the original file. So I can now apply my transmission function that I've just calculated to each one of these. Now this type of transmission function does require a pass energy for each transmission function calculated. So we can't look at pass energy 25 and update that from this data set. So this does require you to use the same percentages throughout your measurements, but I can now apply using the same technique of selecting the file, and let's just check that it did update, and there it is. It's telling me that the transmission function has been updated from revision 2. So that is part of the test. This is now the acid test, and that is, let's correct the spectra and observe how well we get an alignment. In fact, the remarkable thing here is that we've got an alignment pretty much even for pass energy 10, but you can work out the kinks in the background and the transmission to give you something that looks very, very similar to all these other data. So let's just step away from that and close that so we get to see. So yes, this is now transmission corrected data relative to an Escalab 250xi pass energy 40 transmission corrected spectrum. So in principle, all of these spectra should look identical to the Escalab data after they've been transmission corrected. Having calculated these relative transmission function corrected spectra, I'd just like to verify that they really do match the Escalab pass energy 40 spectrum. So let's copy these through to a new file. Make sure we take the processed form. So these are the Nexus G2 spectra after correction for the relative transmission function, and then I need to go and find the pass energy 40 spectrum that I used as the reference spectrum. So this is also transmission corrected, but transmission corrected with respect to the Escalab transmission function, and I'll copy that in. So now I should be able to overlay these and normalize and then do a comparison between the Escalab and the Nexus data. So that's pass energy 10, pass energy 20. We go down the list and we can see that we are indeed recovering from these relative transmission functions spectra that look very similar to the reference spectrum, and that would be a requirement if we're going to obtain the same quantification from these two instruments for the same sample. More importantly, we can use the same relative sensitivity factors for both instruments, and that is a very useful feature of relative transmission functions as I've shown here.